electrons in the outside. Okay, now let's look at some other visuals. Okay, so here is the radioactive source of alpha particles, expected results, the detector, the scintillating screen that the students had to watch and count the hits. We're missing, so the expected results that this beam would shoot right through the gold foil. Okay, I'm going to zoom in if we could. And this is the expected results. Here is the plum pudding model. Here is this matrix of positive that's smeared throughout the entire atom. Because the alpha particle is so dense and positively charged, it would rip right through and not be deflected. Okay, remember, the electrons are so tiny, they're considered to have almost zero mass because they're 2,000 times lighter than proton or neutron. They wouldn't deflect or change the trajectory of a big particle that's 2,000 times bigger. In fact, it's 8,000 times bigger with 2 protons and 2 neutrons. So it should rip right through. What really happened, though, is the actual results is we had some deflections, big deflections. Look at this. Oh, did you see the one over here? Some big deflections that came almost back. Let's wait for it, wait for it, wait for it. There it is. And then you have some here. Now, most of them are still going through, which means the atom is mostly empty space. But if we zoom in, we can see that if a dense nucleus is what happens and it's positive, some will be deflected, like that one. Some will bounce back. Don't make a liar of me. Where are they going to bounce back if they get too close? There it is. Okay, so you get the idea. All right. Okay, so here is a video I play every year, and it's pretty short. It's a little bit repetitive. I hope you get something out of it.
Positive charge in a very small volume, the atomic nucleus. The particles were deflected by a high positive charge in a very small volume, the atomic nucleus. The particles were deflected by a high positive charge in a very small volume, the atomic nucleus. The particles were deflected by a high positive charge in a very small volume, the atomic nucleus. The particles were deflected by a high positive charge in a very small volume, the atomic nucleus.
Yes, the particles were deflected by a high positive charge in a very small volume, the atomic nucleus. Yes, that's the famous. We'll play that again. Okay, we're going to go now to a reference table to show us information about the particles in the reference table. Hold on to your pony. Okay, so this is table 0, okay, table O in your reference table. Okay, remember that alpha particle that Rutherford was shooting out? Well, there it's written in its notation, right there. Okay, and you notice it's a helium. It's a helium nucleus. Now, the top number here is the mass number. Okay. And the bottom number is the charge number. So it has a mass of 4 and a charge of 2. Well, why? Well, the bottom number we also remember is the atomic number. So if you look at a proton, sometimes it has a hydrogen with it because hydrogen has 1 proton in it. That's why it has the atomic number 1. Now, if you notice, the top number is also 1. It has a mass of 1. So a proton has an atomic mass of 1 AMU. It's called atomic mass unit. It's not something we can measure, but it's a relative scale based on the boxes and everything that we've learned. Okay, we know that a mole of hydrogen is 2 grams. Okay, so therefore 1 hydrogen is 1 AMU. Okay, a neutron, and the word neutron is neutral. Look, it has a 0 charge, but it has a mass of 1. So we say that a neutron has 1 AMU. Therefore, neutrons and protons have the same mass. So, if I look back on a helium nucleus, if the charge is 2 or the atomic number is 2, I have 2 protons. How do I get neutrons? Well, if the mass is protons and neutrons, and this bottom number is the charge, or it's usually protons, you subtract it, you get neutrons. Bottom line is, if I have a total mass of 4 and I got 2 protons, I have 2 neutrons. Okay. Now, believe it or not, a beta particle is the same thing as an electron. Used to be written here, and you should write it in table O, electron. An electron, look at that, has 0 mass. Now, that's not really true, but its mass is insignificant compared to these other particles. Why? Why? Because it's 2,000 times lighter. Its charge is -1. So there you go. You have your charges for your protons, neutral for neutron, +1 for a proton, okay, negative for an electron. And then you have the masses. Neutrons and protons have the same mass, electrons. All right, let's go to the periodic table. Okay, on top of your periodic table, you have this written on your periodic table. And notice they give you atomic mass number, goes on top. It's got a decimal place, we'll talk about that, the atomic number. So how do we get protons, electrons, and neutrons from an atom based on the Rutherford model? Well, we know that neutrons and protons have the same mass from table O. So this mass number that I have up here, okay, is telling me that I have some combinations of protons and neutrons that give me 6. This number we've learned already is the proton number. Atoms differ by proton numbers. So we learn that this has 6 protons. No other element has 6 protons other than carbon. Now, what you have to understand though is atoms are neutral. You say the word atom, it's neutral. So therefore the protons, which are positive, like from table O, equal the electrons that are negative to give you a 0 charged atom. Atoms are always electrically neutral. So if I ask you how many electrons in an atom, you would say 6. Negative 6 and a positive 6 gives me 0. Neutrons are neutral from table O. But how do I get neutrons? Well, I know that these two, okay, right here, this one and this one give me the mass of the atom. Well, the mass of the atom is 12, but 6 of those 12s are protons. So to get neutrons, it's 12 minus 6. 6 neutrons. Okay? Now, that's in an atom. Atoms are always neutral. Okay? Now, these things right here are charges that the element loves to become when they become ions. So if you say ion, that means the atom has lost or gained electrons. A little preview as I'm running out of time is that if the carbon atom became -4 charge, became an ion, it would become -4 by actually gaining 4 more electrons, and that would be 10 electrons. Okay, and the reason why it's -4 is, well, carbon, okay, and I'm running out of space, but carbon going to carbon -4 is still carbon. So the proton number can't change because you become negative if you lose positives, but we never lose the proton number because it's still the same symbol. Therefore, you gain electrons. So this has 4 more electrons than normal. So when it becomes an ion, and they list the type of ions it becomes, -4, when it becomes a -4 ion, it had to gain 4 electrons and have 10 electrons. Okay, so in any case, that's a little preview of where we're going. Okay, it got longer. I'm long-winded and I'm tall. Okay, I'll make the form very short though. Thanks. Done.